So let us just try to draw transformers. So we won't do anything new today, I think. We'll just try to draw everything of transformer and we'll try to see how many parameters does it have. So okay, so this we got as xi. What is xi? Input. Okay, and then we had to supply the positional embeddings. So I will drop this now. So let us keep this xi, pi, you add this and then you send it to and there are how many of it? I am fixing this number to be 512, okay, without, I mean t equal to 512 is what I am fixing. So x, so I basically goes from 1 to 512, and then what was happening here? What was happening here? You had self attention. But देखो, I want you guys to help me draw it because there is no point me drawing it alone. Okay. So self attention, and now what? So after self attention we saw, so this self attention and then add and norm. So you have the output of this add and norm. Now what was next? So then this thing is passed to a feed forward network, and then so and then add and norm again. What was the next? Then whatever the output of this, so output of this will go to, we'll look at that. Where are the connections? Where are those short circuits? So what is it that you add and norm? You, whatever these things are, right, whatever the embeddings that you have supplied to self attention, you basically send them here as well. So add and norm. So we first, so whatever the output of this guy is, right, output of this guy and the previous input that you had, you add them and normalize it. You send it to a feed forward network, is that right? Yes. And then क्या चीज? Feed forward के बाद जो add and norm आएगा, हाँ उसमें भी तो एक short करेंगे. हाँ right, add and norm है ना, तो add. So where, what do we add? Where do I short circuit? So this guy goes here, right? So this is my full encoder. And then you can have, if we talk about original transformer, so Pi is not included, of course. So this part you do 6 times, and then what do we do here now? So decoder side you will have same thing here again. So that same thing, you have Xi and then you are supposed to add Pi is there. What were you doing here? What are we supposed to do here? We didn't talk about decoder yet. Okay. So anything in this part that you have not understood? So I have attention is all you need in my hand now. So these are your inputs, these are your outputs. I am still calling them Xi, but you can understand. So these are basically outputs. I mean, outputs means what? Okay, this is something I need to talk about. It says, so input embeddings are fine. These are output embeddings shifted right. And what we have here in the first thing, after positional encoding, you feed it, what you get is a, so masked multi-head attention. After masked multi-head attention, you have that same thing again, that is add and norm. So I mean, instead of making so many arrows, now I just make one. And then add and norm means what? Add and norm means I am going to short circuit. So add whatever was you were feeding as input to masked multi-head attention, after Xi plus Pi, we short circuit it here. So what will you add actually? You will add output of this. Okay. So before computing the next one, whatever is the output here, add it with this one, take normalize it and then go ahead. Right? What was next? So once you have done this, so we are done. Now, so we have outputs here. Now you have here something called multi-head attention. See, whatever non-trivial you do, what do you do after that? Add and norm. Okay. What will we do next? I have I've run out of space now. Feed forward network, then again add and norm, then linear, and then finally softmax. And what will this softmax do? It will give me the probability distribution over next word. So this is what we have learnt in last 6 classes, maybe, how to output next word. Okay. So let us try to figure out more connections here. So this is one encoder, and there are 6 such encoders. You can, there is nothing special about this 6, you can put more or less. Okay. So add and norm, this is fine. Add and norm, what are we going to add and norm here? So what it says is, you have outputs here. Now I am drawing this particular arrow here. So you add and norm. Okay. Now what is left? Everything you have. So add and norm here. What will go to this add? This output? I should have drawn it that side. Okay. What is left? Everything is done. Then tell me what is left. What is left? Right. So right now encoder is doing its thing sequentially in this direction. In this, so every horizontal thing is being computed in parallel. But this way you go in, I mean this way of course you have to go sequentially. You have to compute all these guys, then the output of the first encoder will be sent to the input as input to the next encoder, and you can keep on doing this. So you can stack as many layers of these encoders as you want. Now we are yet to connect encoder to decoder, and where you do it is this. What is the output, I mean what is the size of output of this layer, add and norm? 512. See, this is also called D model. So right now for our examples we are keeping D model equal to 512. Okay. So this is the only point where we connect these two encoders and decoders. And this comes in 6 cross, that means every, so output of, no, so output of whom will be sent to whom? Output of the last encoder will be sent to every decoder here, that is what we had seen. Okay. And which part we did not do? So what are you going to this? What is this layer going? Self attention, we have taken it in detail. Add and norm, we have taken it in detail. And what was add? So why do we need to add in this case now? See, in ResNet, when we talked about it yesterday, in ResNet how many layers they had? Something like 152. Okay. Now, if you have 152 layers, these residual connections are kind of justified. You have 152 layers, but why are they justified in this case? Why would you like to have them here? When would you like to keep these residual connections? No. In which case would you keep these skip connections? When you have too many layers. Okay. Do we have too many layers here? While I can't say no to whatever you say, okay, this is not the reason we keep it here. The reason of these is at least a conscious mind, unless the author explains why have they kept it. In today's world, we keep these skip connections. If you have too many layers, so something might go complicated here. You can, during back propagation, these will help you. Okay, so they won't let the weight decay. They won't let you have this effect of vanishing gradients, because see, your gradient has two paths. So even if one becomes 0, another will become. So this guy will ensure. So see, if you have two paths in your gradients, right, it will be a sum of both these paths. If on one path your gradients become 0, it does not matter, because this path will ensure that gradients are non-zero. But does this solve the exploding gradient problem? No, because in sum, any of these sum, if it is infinity, then so skip connections, they don't solve the exploding gradient problem. But exploding gradient problems are easy to solve. How do you do that? So if grad j is, so if gradients are greater than 100 or whatever number you like, then gradients are 100. Right? So that problem is solvable in just one line. So see, we have said 6x here. So 1, 2, 3, 4. How many layers? 24. Right? So something like that. And now if you go to self attention, is that just one layer? Yes. Self attention, what we were doing here? So पहले क्यों नहीं बोला यार? Thank you. Multi-head. Now multi-head self attention it is supposed to be, but multi-head attention. So thank you. Yes. So because see, you have said this block you can stack as many times as you want. So eventually this can become a lot of layers, okay, which actually in this case are also a lot of layers. And eventually you are passing it to this one. So actually the number of layers will start from here and kind of end up somewhere here. So you already have a lot of layers. 24 plus 24, at least 48 are there. But here you have something more. So here you have something more. Okay. So you have of the order of 50 layers, even if you have just 6x here and 6x here. Okay. हाँ. हाँ. Everywhere where you are being connected from, wherever you are connected, vertically. No, horizontally, all these guys are 512 numbers. Right? So wherever you see these arrows, they are equal to D model, and which is 512 in our case. Of course, you can change it. We'll see GPT has it differently, BERT has it different. Yes. So decoder, हाँ. See, from what we can see in this figure, every non-trivial thing that you do, right, is followed by a add and norm. So what is the question? Yes. So see, this is 512 dimensional. If you want to add it to something, that itself must be 512 dimensional. So this is 512, this is 512, you can add them. Now normalize. Yes. Okay, I need to explain this. Huh? Right? So there is one thing that I have not yet done. We know softmax, we know everything that is here except masked multi-head attention. Okay? So now we talk about that. And then before we conclude today's class, we will also try to enumerate the number of parameters in this model. Okay, so I need to do so let us now try to understand what is going on here. This is certainly not xi, but let us say I call them xi prime and pi prime. Okay. Now, how do we input? What do we input here? What do we input here? Start of the start. So okay, start of the right. So the start symbol, right? So you have start symbol here. What will you finally do? So this goes up, 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 and you predict the next word. Here what we were doing? What was your input here? So right now we are training it. Okay. So you had 512 words here, 512 continuous words from your corpus. Okay. What will be input here? Should I feed everything? See, what is this guy supposed to do? Originally this was supposed to do translate. Okay. So because we are looking at the transformer architecture in the context of original paper where they tried to translate. So this is your target language thing now. Should I give access to everything? What do you think? What is fair to give to model? When you are generating something, is it fair to give what comes next? So you should have everything. So if you are going to predict at tth timestamp, if you are given access to everything before that, that is fine, but I should not have access to t plus 1, right? Because when you are generating something, nobody knows what are you going to see next. You have to generate based on what you have seen in the past. You are not allowed to peep into future. Okay. So Pi, this goes up, up, up out there. You have this softmax output. So whatever your output was, let's say. So you send the start of the start symbol here. It gives you some output. Initially, what do you expect to happen? Remember, we did teacher forcing a few classes ago, right? So what is this guy supposed to do? You output what? You will output a probability distribution. So basically you will output a word. Okay. Now those word embeddings you feed here, and the next output, and whatever the output is, you feed in the embeddings of. So what is it that you are actually feeding, the word or its embeddings? Clearly embeddings, there is nothing to talk about there. So, and this way you keep on doing. The only catch is you are not supposed to know what comes next. Okay, that is something you are supposed to predict. So I am not trying to do this, that predict what comes here, but you know everything before it and everything after it. That is that you might call. So that might be a legitimate problem to solve, but that is not a generation problem. Okay, so we don't do this. Now, so this is fine, this is fine. Now, so how do you implement this, that I should not be able to peep into future? How do I implement this? See, this is multi-head attention, so something similar might be going on, right? Now, how do I stop it from looking at the next words? So what was our multi-head attention? What was the equation for this? This was softmax Q transpose K divided by under root dk V, right? Now, your masked, of course it is multi-head, so let me make sure, yes it is multi-head. So masked attention is going to be softmax, right? This makes sense. So the output of softmax is what you want to make 0, or what you add is you want to make 0. So let me finish writing this and then I'll ask the same question. So Q transpose K divided by root dk plus m v. So note that these two equations are basically the same. Right. So these two equations are basically the same, you have just one difference here, plus m. Now what should this m be? What should this m be? A matrix or a number? Matrix. If matrix, what are the dimensions? So what was this whole thing? This whole thing, if I remember it right, was 512 cross 512. Check it out. Right, because you have to get 512 values for every input. So, right. So this was 512 cross 512. So m must be, right. So this was 512 cross 512. So m must be 512 cross 512. This guy is a scalar, so that's okay. What do we do now? What was V, by the way, for completeness? 512 cross 64. Now, so we are done with the dimensions. Now what? What should be the entries of matrix M? Negative of QTK, right? That makes everything 0 and I am done. What will be the impact of having everything 0? No, but if everything is 0, so if Q equal to minus Q transpose K, everything is 0. What will be softmax of every 0 vector? No, it won't be 0 because e to the power x is never 0. So it will be a uniform distribution, e to the power 0. So everybody is e to the power 0. So you have 1 upon 512. So you have assigned uniform probability to everyone, which is, of course, I mean, we don't have to do all this to assign uniform probability distribution. So what next? So m is not negative of this. If m is 0, you are back to the normal multi-head attention. Okay. So what should m be? So let me write here. So by the way, a lot of it is also taken from, so let me just say it. So you may write this down. CS 480/680 lecture 19, attention and transformer networks at Waterloo University, University of Waterloo. Okay. The instructor is Pascal Poppert. So M is a mask matrix of zeros and minus infinities. So now can you tell me where to put 0 and where to put minus infinity? So M should be what? So it's a 512 cross 512. What should my diagonal be? So you say my diagonal should be minus infinity. Why so? Okay. When you are outputting the first word, you don't want to look at, so what will be the impact of minus infinity? So if I have this 0 and rest minus, rest everything is minus infinity, what is it? So we go and look somewhere here. So what is going to happen here? See, important here is, even though we have not written anywhere here, but this multi-head attention inherently calculates a softmax inside it, right? So we are not talking about that softmax out there. We are talking about the softmax that you are computing to take multi-head attention or mask multi-head attention here itself. So there is a softmax here inside this box. It is that softmax that we are talking about. So what will be the impact of, all? So how should my first row look like? What is the impact of minus infinity? Guys, what is the impact of minus infinity? So in softmax, you will have e to the power minus infinity, that makes probability of that term equal to 0, and that is what you were looking for. Okay. So what happens to the first, this guy will get multiplied with, so if you see here, first column will multiply with what? This is 512 cross 64. So how many values do you have? 512. Okay. So value of first should depend on what? See, you are not allowed to do, you are not allowed to look at future things. Here we could easily do that. So here while computing this output, you take Q1 here, K1 here, dot product, and Q1 here, K2 here, dot product, and so on. But in this case, do you want to have a look at Q1 dot K2? Because K2 is coming from the next word here, and you don't want your model to have access to those values. So what do I do? So what will be my first word? First word will be Q1 dot K1, and whatever the next term was, that should be minus infinity. So this should be masked. When you are generating output here, when you are generating output for first of these 512, you are not supposed to look here. What does that mean? That means you are supposed to compute Q1 dot K1, I mean take transpose wherever necessary. So Q1 transpose K1, you compute that, but are you allowed to do Q1 transpose K2? You are not allowed to do that because K2 comes from here and we are saying these values must be masked. You don't know anything about them. So when you want to output V1, what should it be? What should M be? M is here. So M should be 0 for the first term, but minus infinity for everyone else. So now you get what the matrix is? Right. So this is 0 and remaining, how many minus infinity is here? 5, 1, 1. What will be the next? 0. Now you are at the second term, so you are supposed to do Q2 transpose K1 and you are also allowed to do Q2 transpose K2, but not anything else. And so on. What will be my last term? So in last one you are allowed to do Q512 transpose K1, Q512 transpose K2 all the way until 512. So this is your M. This will be minus infinity here and everyone will be 0. Right? So this is your M. You add this M here. So wherever you are allowed, you are making this M 0. That means you are going back to whatever this Q transpose K was. Right? But wherever you are not allowed, so this guy now takes care of which part? If you are allowed, you remain to what original things were. When you are not allowed, M comes into picture and puts a minus infinity there, which assigns a probability of 0 in the output of softmax. But where? Which softmax? Here only, not that guy. That guy is giving you the final output probability distribution. So we are not talking about that softmax. There is a softmax sitting here inside this layer. Okay. So this part is done. What is left is what are we doing here? So I may not be able to do the number of parameters here in today's class, but that's okay. So what do we do here now? What happens here? Yes, what is the final step left and we are done for today? By the way, one more thing. What does this layer exactly do? Add is fine. So I have added and then you take the norm of it, right? What next? So when you normalize, what do? Your numbers change, right? So whatever was the input, that will change to, so the number changes to original input minus mean divided by sigma, which is your variance, right? So what is this normalization doing? What was it? I am not writing those same equations that we had written yesterday. So if xi is the input, so whatever is this, what will xi become? So xi hat will become xi minus mu divided by sigma, right. So, every term changes from whatever it was. So, before you compute normalize, so before you normalize, everything was x12, x512, and after normalization everything changes to xi hat in this manner. Now, what might be wrong with this numerically? Sigma may become 0 and you may have issues like division by 0. So, this is what you essentially do. Where epsilon is a very small number greater than 0. I mean, okay, this is more like E. Done? We are done too. Last thing, what was that? So, this is the final output of your which layer? Add and norm. So, your add and norm is giving me outputs like this. What are xi's after add and norm? Xi's are those guys that are output from the previous layer and feedback coming from the add thing. Add both of them, you get xi, and that you convert to, so basically that you normalize to this. So, right, but just a few seconds thing. So, you output the first word. During training, what should you do? You should send that same output as a feedback here, or you should input here the correct word because you have training data with you. How many of you don't get my question? So, my question is, I start with the start symbol. This is eventually going to give me a probability distribution and finally a word that I have to choose, the one with the maximum probability. I choose that word with the maximum probability, whatever it comes out to be, right? Should I feed the word embedding of this output here to this guy, or should I feed the original output in my data set? Output? And what is wrong with this? Right. Right? And initially when you just started your training, all the weights here are random. So, most likely this first output will be random. Okay? So, you use that output to compute the loss. Okay, one thing we are missing, we have still not done the loss part of it. So, you compute the loss using your actual output that you had put, but input is what you feed as, what do you feed as input? Whatever is the right word in your data set. Once your model is trained for long enough, you can actually start feeding whatever the output was. So, this thing that we have done initially, what is it called? Teacher forcing. Okay, we saw this in terms of RNNs too. Okay, done for today.